Hello everyone, welcome to my presentation. My name is Wang, and now I am a PhD researcher at the University of Nottingham. My research topic is about the optimization of energy efficiency for HVAC systems in offices, buildings, and metro stations. Today, I'm going to talk about the integration of deep learning approach and predictive load models for real-time, low computation cost room energy load estimation. Now, let's get started. Let's look at the first part of this presentation. To start with, I would like to briefly talk about buildings' energy consumption and what is HVAC systems. Buildings are one of the largest energy-consuming sectors globally. In particular, heating, ventilation, and air conditioning systems called HVAC systems account for most energy consumed in buildings. How to reduce the energy consumption of HVAC systems is one of the most important research topics. This figure shows a building with typical air conditioning system. The air conditioning system is responsible for offering occupants thermal satisfaction. That means occupants would be satisfied with indoor air temperature and they wouldn't feel too hot or cold indoors. This is good to increase their productivity and improve their well-being, but generally the cost can be high electric energy consumed by the system. So it is very necessary to balance the trade-off relationship between occupants' thermal satisfaction and the energy consumed by HVAC systems. Based on literature review, it turns out that adopting an optimal HVAC set point temperature is the key to solving this problem. However, we realized that internal heat gains could influence the optimal set point temperature decided. In previous study, the internal heat gains from occupants and equipment were oversimplified. The internal gains from occupants and equipment were assumed to be constant or zero. This is reasonable, but in fact, human behaviors are complicated and it is almost impossible to exactly know, predict, or simulate how internal heat gains vary with time. According to building guides, occupants and equipment were heat sources rejecting heat to indoor environment. The amount of heat rejected to indoor environment could affect the energy consumption of the HVAC system. Furthermore, internal heat gains could cause a change of optimal set point temperature determined. Therefore, in our previous study, a camera based on deep learning approach was developed to detect and identify the real-time internal heat gains. This is a short video showing how the camera worked. The camera was based on convolutional neural networks, and the camera was deployed in a seminar room at the University of Nottingham. You can see from the video, there were two charts here. The first one is the number of computers on. The second one is the activity of occupants. Based on images captured by camera, real-time internal heat gains were obtained. For more information about the cameras, please follow our previous work showing here. The generated real-time internal heat gains from the camera are shown in the left figure. You can clearly see how equipment, occupants, and total internal heat gains varied with time during the monitor period. The right figure compares the total internal heat gains with the static internal heat gains that is widely used in literature. It can be seen that internal heat gains in literature were overestimated. These slides demonstrate our real-time optimization framework. This framework is aimed at optimizing the HVAC set point temperature in order to achieve a balance between energy consumption of HVAC system and thermal satisfaction of occupants. It is composed of 6 modules. The first module focuses on capturing and identifying images by cameras. The second module focuses on generating real-time internal heat gains profile. Now these two modules are finished. The module 4, 5, and 6 was still under investigation. For the rest of this presentation, I will mainly talk about the module 3, how predictive load models were developed for real-time room energy load estimation. Welcome to the second section of this presentation. This section is about the methodologies used to develop predictive load models. In the module 1 and 2, the internal heat gains were calculated every 10 minutes. In order to use the real-time internal heat gains from camera and achieve real-time load estimation, we need lightweight models that can have low computation cost. In other words, traditional white box models based on thermodynamics were not a good option. Instead, shallow neural networks as a kind of black box models were chosen. The dashed box shows our models developed offline. We started with collecting two different internal heat gains profiles. Then the building energy simulation tool, called IES, was used to simulate the energy performance of the room where the camera was deployed. After that, the simulated data were used to train, validate, and test the models. During this process, static internal heat gains profile was used. But please notice that even if the models achieved high fitting performance based on training, validation, and test datasets, we still need to further verify the reliability of the models. We still need to make sure that our models correctly learn the complicated relationship between internal heat gains, HVAC set point temperature, and HVAC energy consumption. That's why we further design a verification part using the real-time internal heat gains profile. After the development and verification process, the models were finally established. This slide shows the architecture of our models. The models were developed using the MATLAB neural fitting tools. To keep the models lightweight, there were only 10 hidden units in the hidden layer. For more information about the architecture and parameters of the models, please see the MATLAB official website. In addition, we also conducted a parametric study to find the best models. In this study, we considered two kinds of different models: linear regression and shallow neural networks. Also, the number of inputs was taken into consideration. For the case 1, 3, 5, 7, only 6 inputs were considered. They were outdoor air temperature, wind speed, direct radiation, diffuse radiation, internal heat gains, and HVAC set point temperature. The other two inputs considered were annual and daily time step, representing the time sequence of the day. Based on trial and error method, we found that adding these two inputs can significantly improve the fitting performance. This would be shown shortly. Now, let's look at the section 3 of this presentation, the developed predictive load models. The result of parametric study is shown in this slide. It can be noticed that a shallow neural network had higher fitting performance than linear regression models. In other words, linear regression models may not be able to learn the complicated relationship between internal heat gains, HVAC set point, and HVAC energy consumption. Furthermore, as a result of adding 2 extra inputs, the shallow neural networks with 8 inputs in case 4 achieved much higher fitting performance than case 3. Based on this figure, we can say that shallow neural networks with 8 inputs were the best models for heating and cooling load estimation. We further verify the models developed by using the real-time internal heat gas profile, because again, we wanted to make sure that our models were able to learn the complicated relationship between internal heat gas, HVAC set point temperature, and HVAC energy consumption. As can be seen from the figure, even using the real-time internal heat gas profile, our models had fitting performance higher than 0.85 over the 10 verification scenarios. These figures compare the estimated and simulated room heating and cooling loads. It can be seen that the estimated room loads were close to the simulated room loads. Now, because the shallow neural networks with 8 inputs achieved high fitting performance both on development and verification datasets, we can conclude that the shallow neural networks with 8 inputs were just the models we were looking for. So finally, the predictive load models were successfully established and they could be used in the future. Now, the real-time predictive load models were built already and the module 3 was finished. The future work would be developing predictive comfort models and set point optimizer. Now, let's come to the final section of my presentation. In this presentation, we firstly reviewed vision-based cameras for obtaining real-time internal heat gas profile. Secondly, we shortly introduced how 2 predictive load models were established based on shallow neural networks. Because the developed predictive load models were lightweight, they can be easily integrated with the real-time internal gas profile from cameras for online room loads estimation. In the future, predictive comfort models and setpoint optimizer would be developed. In the end, this would be combined all together to achieve a real-time balance between HVAC energy consumption and occupants' thermal comfort. That brings us to the end of my presentation. Thank you for your listening. If you have any question or feedback, please feel free to contact us. We look forward to seeing you